Okay, good afternoon everyone and welcome to this IMU organised discussion panel on machine-assisted proofs. My name is James Davenport and I'm the moderator. You have here the list of speakers in the order in which we're going. My aim is that the speakers take about half the time, then we have half the time for questions from the floor. So if you, when it comes to question from the floor, please raise your hand and I'll try to ask one of our staff to get you the microphone. So there's a very brief and partial history of what you might mean by proofs and the large proofs of if required machine assistance. Either Lefite-Thomson, Salzburg Roots for Order was published in 1963, but then again in 2012, Gontier and Terry has stated they had a formal proof of it, which is interesting. The very large proof for every planar map was four-colorable was produced in 1976. A lot of computation and 256 pages of paper proof, the revised proof and so on. There's then of course the famous Hale's proof of his Kepler conjecture, which you see was published uncertified by referees in Annals of Mathematics, and so on. Then in 2013, Harald Helfgott, was one of our speakers, produced his proof of the Ternary-Goldbach conjecture in archives, so there's not a question of certification, of course. In 2014, the Fleischbeck project announced had a formal proof of the Kepler conjecture. 2016, James Maynard published his paper. In 2017, the Fleischbeck project actually published its final paper, describing, as it were, and pointing to the formal proof. So those are various things we've seen happen, and the purpose of this panel is to discuss these events and what they might mean for us, where us means implications for authors, implications for journals and publishers, implications for the refereeing process, and also implications for readers. So those are the sort of questions we shall be looking at during this panel. And now over to our first actual panelists, Bjorn Poonen.
All right, thank you. So I'm going to talk, I'm mainly going to just raise some more questions. So let me start by thanking my colleague Andrew Sutherland, who's done a lot of machine computations himself. All right, so first of all, there's several different ways in which computers have been used well, both for proofs and for figuring out what should be proved. So first of all, the first way in which maybe they're used is as experiments, to carry out experiments to figure out, to test new conjectures or to figure out what the conjecture should be. And so this is a very old use of computers. For example, well, in the 1960s already, computers were used to come up with the Birchon-Swinnerton-Dyer conjecture, which is one of the Clay millennium problems. And that's probably not the oldest example either. So the second way in which they're used, which is maybe a very common one, is that humans will reduce a proof to a large number of cases, as in the four-color conjecture that was mentioned. And then, well, then the computer does all that instead of what you would do in the old days, where you just say, well, this is left to the reader, or something like this. All right, but and more recently, there's the notion of formal proofs, where, well, one thing you can do now is for some proofs you can enter them you can type them into a language that the computer can check. So the computer can check all the logical deductions, and there's some, I think we'll hear more about this later, but there's some proof assistance that can help in generating, in doing this conversion process of transferring sort of a human proof into something that the computer can check. And finally, well, maybe the ultimate is that the computer actually finds the proof for you, but well, anyway, that was, well, maybe we'll hear about some of this as well. Okay, so I want to mention a couple of things that have changed in recent years. So one thing that's changed fairly recently is the onset, well, the availability of cloud computing services such as the Amazon Web Services and the Google Compute Engine. So what these are, these big companies, they have lots of computers that they're not using all the time. So they rent out the computers effectively to anybody who wants to use them. And for example, my colleague Andrew Sutherland, he did a 300-year computation in 8 hours by just using lots and lots of computers. I mean, the way it works is you're not guaranteed that you're going to get them all the time. Google reserves the right to like grab your computer during your computation, and then you have to start over. But if your computation is such that that's okay, well then you can just do it. I mean, they charge something too, but the amount they charge is pretty close to just the cost of the electricity. So in fact, maybe it's actually much cheaper to do one of these computations. If you have a really big computation, it's very likely that it'll be cheaper to do it on these with these services than to do it on your own computer. Yeah. Okay. And yeah, and this, as Andrew Sutherland says, this can really change the kind of questions you try to investigate if you know that you have the ability to do this kind of computation. And also another thing is that there are a lot of large databases in various fields. So in number theory, there's the L functions and modular forms database that contains huge tables of elliptic curves and modular forms and other things. And and many proofs are based on the data that's in these databases. And so then there are all sorts of questions about, well, how reliable are these databases and so on. There are very many issues that come up in refereeing as well. So almost all math journals, at least some of their papers, involve machine computations. And so, well, I'm not going to try to answer all these questions. I'm just trying to bring them up so that, and then hopefully people can ask questions about them, or maybe some of them will be answered by the other speakers. So first, you can ask, should machine-assisted proofs be considered suspect any more than human ones? Maybe they should be considered less suspect because sometimes, well, depending on the computation, the humans might make more mistakes than the computers. And what if you have a referee who's not qualified to check the computations, or they just don't feel like doing it, checking computations? What do you do then? Or maybe if it's one of these huge computations, maybe that's just too expensive. I mean, if you've done a $20,000 computation, and you're the referee, I mean, do you really want to ask the referee to spend $20,000 to check it again? Maybe not. And what happens if the computation involves software where the algorithms are not made public? So there are many computer algebra packages that are this way. And so what do you do about those? So you could ask, should you only insist that all the software that's used be open source? Or even should the software itself go through a peer review process? So there's some computer algebra packages that have this, where each new algorithm that's inputted, it has to be checked by somebody else. And then finally, how should the proofs be published? Should they just be attached online, or should there be a print version, or what? So I mean, some of my own opinions are that the standard should be similar to publishing a paper without computer input. So really, the authors should present their proofs in a way that's understandable and verifiable, so that for the future, if necessary, people can go back and check it. And so the burden really should be on the authors to make their computer code verifiable and understandable. So they should have comments and so on. And ideally, eventually, even if it's not generated this way originally, it's nicest if the code is written in some high-level language where the computer program itself is something that somebody without computer experience can actually read. So you could say like, let S be the symmetric group on 100 letters and things like that. And there are many computer algebra packages are this way, where you can work with high-level objects they're very close to the actual mathematics. Okay, so I think that's all I have to say. So I'm going to pass the microphone on to Maynard.
Okay, hello everyone. I want to talk a little bit about machine-assisted proofs from a very personal perspective. So, I guess similarly to Bjorn, I want to mainly raise questions, but also talk through a couple of examples where I've experienced this. So for context, I'm a number theorist. I don't work in formal proofs. I don't work in computer science. I wouldn't count myself as particularly computer literate, although I have used computations in a few of my pieces of work. None of them have been very large-scale computations, but even my limited experiences of computations and using computers in proofs, I think touches on some of the challenges that we're going to experience as a community, which are only going to get bigger as time goes on. So, very roughly, I want to point out that there's huge opportunities that computers can provide us as mathematicians to help us with proofs, but also, naturally, the increasing use of computers is going to present several challenges and difficulties for us as a community. So, from my perspective, maybe these are the three key opportunities that computers present. And although this maybe sounds like a slightly pedantic point, I actually find that the most beneficial way in which computers help me is just in guiding me to what the right conjecture should be, the right proof of the lemma, the right statement of a lemma. So in my day-to-day mathematics, I'm using my computer all the time to plot graphs, to guess inequalities, to test out cases. I guess one potential precise statement of a small lemma that I want to prove in my result, and I use my computer to test 1,000 subcases, and half the time my computer will very quickly come up with a counterexample, and so I don't need to waste a day trying to prove the incorrect formulation of the lemma that I previously had. So I view this as amazingly helpful, and although this isn't actually taking a formal role in actually producing a proof, guiding the intuition is absolutely vital for mathematicians to come up with a proof, and even some of the amazingly high-level people in our subject, so André Weil, for example, who you maybe think of as a very theoretical, abstract mathematician, always emphasized the point and the value of going through many, many different examples to guide your intuition. And we're in a very fortunate position now that we have computers which can simply go through many, many more cases than you can possibly do by hand. Bjorn already mentioned the L functions and modular forms database, which for number theorists is a huge resource because it's exceptionally difficult to do some of these computations, but we can very quickly go online and find huge tables of data to check for patterns in the sorts of objects that we're looking for. So in my mind, the biggest benefit to computers is just this personal assistant for guiding intuition and checking hypotheses. But obviously they can do more than just be an aid to your theoretical proof. They can actually help with the proof themselves by performing large computations, checking many cases. Maybe in the future, they'll go beyond simple computations or maybe manipulation of algebra, but one could easily imagine cases when computers are able to start proving small statements themselves by having developed enough of a mathematical language to be able to fill in the details of small parts of results, and this could again be an exceptionally useful tool. But particularly in difficult problems, a very natural mathematical approach is to split it into many cases, deal with each case separately. In questions like the Four-Color Theorem, this quite quickly becomes exceptionally difficult, even if it's still a finite problem, and so computers provide a get-out clause and a way of proving results that would otherwise be inaccessible just for human time limitations. And then the final part is for formal verification of proofs. I'm sure we all know of various different examples of results which are initially believed to be correct, but have subsequently turned out to be incorrect. There have been issues in various proofs, and as mathematics as a subject grows, we naturally rely on previous results more and more and more. And so it's natural and important for us to always be checking our foundations, and so far we've been doing this purely from a human perspective in general, but being able to rigorously and formally verify proofs as being correct is certainly going to be a useful tool if we can start making the formal proof checking language sufficiently easy for a general mathematician to use so that we can have a bit more confidence in the results as we gradually build up the field. And we don't have to worry about the foundations of the results that we're relying on. However, in the opposite direction, all of these new uses for computers certainly present several challenges and difficulties for us as a community. So I just want to raise a few general potential pitfalls before talking about a couple of explicit examples, both in the positive direction and the negative example direction that I've experienced. So one obvious challenge is, are computations actually rigorous? We can get a computer to try and perform various computations, but we need to be very careful about how accurate these computations really are if we want to make sure that our results are genuinely completely correct. There can be flipped bits caused by solar flares and things. Even if you have a completely working computer, this can cause errors. Even if you're using error correction on your memory and things, this only has a certain level of reliability, which can potentially become more and more of an issue as you're doing bigger and bigger computations. One has to obviously be very careful if you're not using exact arithmetic at any point. I think there was a bug found in the microcode of an Intel processor thanks to doing mathematical computations, but this means that the processor itself had a slight flaw, and it's certainly unrealistic for the referee to have to not only peer review your computations, but peer review the processor that you are using for the computations. So how rigorous the computations are is certainly an open and potentially difficult problem, but alongside that, in my mind at least, a proof is not simply a formal list of statements which formally, logically gives the conclusion that we want. Proof, in my mind, is very much a social thing where it's communicating the ideas and the mathematics behind those ideas. And obviously, rigor is important, but whenever I look at another piece of mathematics, I'm not interested so much in the formal verification of it as the ideas behind it and the key mathematical content. And simply having a formal computer-generated proof or some huge computation that deals with lots of subcases does not generate any understanding in the mathematical sense. And so we need to be careful that we don't start producing a long list of correct statements that have no mathematical understanding behind them and therefore will not lead to anything beyond them. And the final point, which maybe I'll touch on a bit later, is how do we find errors if there is a mistake or a bug in someone's code, either because it's not written properly or because there's a problem with the human-machine interface or there's a problem with the machine. We need to have some way of checking for these errors which is going to naturally fit in with the current human refereeing process. So just to expand on these, I'd like to give two examples of cases in my research where I have used computation, and hopefully they'll highlight some of the opportunities and benefits of computations, but also some of the pitfalls. So one positive direction, which I've used a few times in my research, is that I want to understand the spectrum of some infinite dimensional linear operator. And unfortunately, we don't seem to have very good mathematical tools and analysis for understanding this in the sort of specificity that I needed for my research. But if we reduce the whole problem from an infinite dimensional space to a finite dimensional space, then the linear operator essentially just acts like a matrix, and this is the whole question is just understanding the eigenvalues of a matrix. And so if I can understand a good finite dimensional subspace, which is closely related to what I guess are the large eigenvalues, then I can reduce understanding getting bounds in the spectrum of this linear operator into understanding this finite piece, just the action on this linear subspace, which is then just calculating eigenvalues of some explicit matrix where I can compute all the entries and I can just use a computer to understand the eigenvalues. And so this idea has cropped up a couple of times in my research, and I found it a very powerful thing I have a general theoretical mathematical object, but I reduce it down to a finite mathematical object where I can then just do explicit computations and I can get the computer to understand things when I don't have the theoretical toolkit to be able to explicitly understand it myself. And here there's a very nice marriage between non-rigorous computation and rigorous computation that often I need to guess a good lower dimensional subspace and guess a approximate eigenvector or something like that. I can do this using quick and dirt and cheap non-rigorous computations, and then I can verify everything using exact arithmetic and just using integers and real numbers, so there'll be no round-off errors, and I can be much more confident about the lack of errors in the computation. And there's also then a happy trade-off between the quality of the bounds I get on the spectrum and the amount of computer time that I'm using. So this is one example which I found very useful. It's something that I really couldn't say anything at all about without having a computer, but it's enabled me to produce explicit bounds which have been good enough for my applications using formal arithmetic, and even though maybe if I'm doing a larger computation it's not so realistic for someone to immediately verify on their home computer, it's very easy for them to verify the code by doing a smaller scale version of exactly the same computation, just by changing one parameter in the code. Another way in which computations have appeared in my research, and also when I've been a referee, is in a slightly different context, which has actually caused a few problems and made me feel slightly uncomfortable about how we currently deal with things. So I'd like to raise the second example as maybe a more negative example. So it's happened several times in my research that after doing various theoretical manipulations, I'm left with some, in principle, explicit, but very messy, high-dimensional integral, and I want to just calculate the numerical value of this integral and show that it's less than 1. And unfortunately, my computations that as they currently stand, which I've used and have appeared in journals, are not completely rigorous. Now, I have full confidence in them, but I'm not using exact arithmetic here. This is partly because of the difficulty of finding I searched and I failed to find a suitable exact arithmetic numerical integration package that would be suitable for this. This is unfortunate. I have no doubt whatsoever that the computations I'm doing are giving me the correct answers, but as it stands, they're not rigorous, and this is the current accepted standard for journals. I've also been a referee for similar papers, and again, it's accepted that the computations are not completely rigorous here. And whilst maybe these specific examples aren't the most concerning cases, this is clearly not a perfect situation, and it can only get worse as these cases could become more common in journals and research in the future, and we need to decide as a community where the threshold should be and in what manner we should do it. And it's already getting to the stage that we're getting some results which are not quite rigorous, and we need to be very careful about how we proceed. The second part is on the refereeing side. When you're refereeing computer code, sometimes these codes for the messy integrals are exceptionally difficult to referee because there's a huge number of sources of error. If you make one typo in just writing down the explicit integral that you want to compute, then it will only change the result very slightly, but it's almost impossible for any human to verify this because there's any small digit change suddenly can change the actual numerical result that comes out. When I referee a paper, I can read the statement of a lemma, and I can normally guess whether the lemma is correct or not, and I can fill in the details myself without having to read every individual letter. Whereas for numerical computations, every single digit matters, and one small typo is almost impossible to detect. So I think I'm going to stop here, but I'd like to raise these as issues that, as a community, we're going to need to think about more and more in the future. And I'll now pass on to Harald, who's the next speaker.
All right. Very well. So, of course, machine-assisted, as several speakers have already said, can mean any of several related things. So there is exploratory work, and their standards are lower. Then there's machine assistance in the course of the proof. In analytic number theory, that means, as James said, mainly rigorous computations and casework. And number three, and I will barely touch upon that point, there's the production and verification of formal proofs. Even the production of formal proofs in practice has to be machine assisted. So there are several issues that I would like to discuss. So what is a rigorous computation? Are computer errors at all likely? Well, and many times what we call computer errors are really human errors in dealing with computers. How do we check for errors? I mean, that's an issue even when computers are not involved in the proof. Can computers help? Certainly we would like to use machines to make our proofs more reliable rather than less so. And the last point, which is really a point for the panel discussion, is what the meaning and purpose of a proof should be, besides establishing correctness. And how does the use of computers affect that? So let me be rather concrete. This may be familiar to many of you, but perhaps less so to others. So of course, when we do exploratory work, we hack out happily sign of blah, 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 what is this, times, plus. But in fact, a computer cannot possibly store a real number, a generic real number, that would take an infinite amount of space. So obviously, what we have to do is somehow work with real numbers without working with real numbers. What a computer can deal with are rationals, ideally rationals whose denominators are powers of 2. So one very practical way of doing that is to use interval arithmetic, where the basic data type is not something that pretends to be a real number, but rather an interval in the real numbers. An interval, a comma b, where a and b are rational. No? And then you can work with, you can implement functions defined in the real numbers by seeing what they do to intervals. You say that a procedure encodes a function if it's telling you truthfully the answer, if it's telling you a truthful answer to the question, what happens to an interval when it's mapped by a function or a direct product of intervals. It gives you an interval containing the answer. If you give to the computer an interval containing your real number or real numbers, then it will give you as an answer an interval containing the mathematical answer. And that works out quite nicely. That was first proposed in the late 1950s, and there are plenty of implementations of that. They have been used over and over. There are small variants of that. The one problem with that, which is not an enormous problem in my view, is that it does tend to increase running time considerably, though in our days not catastrophically. A rather good implementation will multiply running time by about 10, sometimes a bit less. So an example of a large-scale application, well, if you ask up to which height has the Riemann hypothesis been verified, that doesn't have one answer, but I would like to say that the answer I'm satisfied with is that provided by David Platt, because he used interval arithmetic to check that all the zeros up to 1.1 times 10 to the 11 have real part 1/2. Well, some people will tell you, well, why multiply running time by 10? You could simply keep track of rounding errors by hand. But my feeling is that that's practical only for rather short programs. And I see that there has been some error in human-machine interaction that has deleted the line opportunity for human error. Well, that's a self-referential sentence and intentionally so. All right, let me give you a few more examples. So interval arithmetic is actually quite useful in making some other things rigorous. So on a day-to-day basis, we might be satisfied with, proof by GNU plot, as in, oh, I want to see that this function is bounded by 2, I plot it. Yeah, it's bounded by 2 in this interval. Of course, that's no proof, even if it convinces us, but there is a way to make that, to automate that process so that we get, so a computer proves that this is actually correct, so that it doesn't just show the truth to us. It's actually quite simple. So that's what we want to show. And in a proof, what you can do is use the bisection method quite simply. And it's very, very, very simple. It's a few lines of code to implement it using integral arithmetic, so it's actually rigorous. Now, sometimes when things become rather close to each other, you want to compare their derivatives in the neighborhood of the place where they are very close to each other or where they become equal. But it would be nicer if that were also completely automated, but we are not far from being there. Not at all. And the same was locating maxima and minima. No. Now, numerical integration, that was mentioned by James. So in my work, I would like to say that I do rigorous numerical integration. That's not really my merit, it's the merit of the people who wrote the programs. It's not pleasant, but I would like to say that by now, it's my opinion that we should have the standard that it's not really valid to say in a paper you submit, well, this integral is such and psi by Mathematica. You should say a bit more than that. There are processes for rigorous quadrature. So even if you're convinced increasing the error, decreasing the tolerance, if you're convinced that the answer is converging to the correct result, I don't think that's good enough. There are ways to make integration rigorous. There are problems. I mean, if the integrand is differentiable, it's really all quite simple and straightforward. But if the thing is not differentiable, or even if it's real differentiable but not analytic, it can be a headache, and this process should be automated. It isn't. It involves some ad hoc work. But you can make, I know of at least 2 computer programs that can more or less deal with that, and they are improving rapidly. So the nastiest integral I had to deal with was something like this. It's not so nasty. I mean, it doesn't look so nasty, but the only way, so, you know, in the paper I claim, this is really a correct result, and the computation is rigorous, but the way to compute it, well, as of now, as opposed to 3 years in the future, say, you cannot just key it into the computer. You have to, you know, ask the kind author of the computer package to improve his package so that it can deal with this. And then you toy with his program and you run it overnight, and it gives you an answer with yes, it certifies what it gives you a bound for the error term. After you toy with the parameters, it will give you something quite reasonable. Yes, I should also say that once computations get large enough, computer scientists should be happy, because it stops being a matter of programming well. It starts being a matter of how good is your algorithm. That's much more important than whether you're a good programmer. And that makes me happy, because I suppose I'm pretty good at algorithms, but as a programmer, it's just like cooking. It's a survival skill. And that comes up quite a lot in analytic number theory. So people talked about large computations, casework. What is typical in analytic number theory? Very often, by analytic means, we manage to show that a certain expression, an arithmetic expression, is of the form f of n plus an error. And the error is bounded by g of n. And g of n is much, much smaller than f of n, well, eventually, when n is large. When n is small, the results might not be very good. G of n might not be much smaller than f of n, or the result might not be valid at all. And so you have to complement it with computations. So, yeah, so what you do is you complement it that way, and to encapsulate those computations, to give them in a nice closed form, you know, you find a bound that is obeyed by all of them. To give you an example, say m of n is equal to mu of k over k. I mean, if the Riemann hypothesis had been proven, then it would be easy to prove unconditionally that this is of size about well, log n over square, well, at least log n over square root of n. For sharper bounds, we would need more information. Now, the best result I know of that is unconditionally is a bound by Ramaret, which gives you a bound that is actually quite nice when n is quite big. When n is not quite big, well, fortunately, there are only finitely many not quite big numbers, so you might as well use a computer and check that. That was the largest computation I carried out for the book on Ternary-Goldbach. Actually, you know, I would have been satisfied with 10 to the 10, but 10 to the 14s I could do in a couple of weeks in a desktop, so why not? And then you can put these two together to give a nice bound that is true for all n. So that's a typical computation in analytic number theory. No, and here it's obvious that you can do it in linear time, but in general it can be quite interesting to show that you can find an almost linear time algorithm. Or almost linear time, and log n. And at some point, in fact, sometimes you have to stop your computation because it's taking too long, and sometimes it's because fast interval arithmetic has its limitations, the errors start to accumulate, and you realize that you have to stop at a certain big N, or else the error is just going to degenerate. So that's just to give you an example of a practical issue. All right, so people talked about computer errors. I trust computers much more than I trust humans. So the only problem is that computers do whatever we tell them to do. And people talked about neutrinos and the like, yes, cooking, doing something nasty to our computations. In practice, being realistic, that's going to be an issue only for the largest of computations, eh? And also, again, unless you have a very large computation, the easiest thing in verification is to just run the program again and again, possibly on different hardware and software. So I think one can reasonably ask that of the referee if it just takes a few 10,000 hours. Yeah, if it were 1 million hours, or a couple million hours, and as in the computation Bjorn referred to, that's a different issue. And unfortunately, once you get to the, I would say, once you get to the million-hour core hour mark, it's there that checksums are going to tell you that maybe there was one mistake somewhere. Yeah, I didn't get to that scale. All right. So the actual issue is human error. Errors in programming, and errors also quite simply in copying input and output. We would like, that sounds very silly, but people make mistakes like that all the time. Me too. It's also the case that humans make mistakes when they don't use computers. And since we are going to use computers to control computers, we might as well use computers to control us. So my current practice is at first I program a great deal, but then when I submit the thing, then I try to minimize the number of programs that are actually used in the text and keep them short. And for really time and space intensive computations, it's not realistic to use, well, Sage or Python or what have you. I have to use C, which is a bit harder to read, but I try to make it readable enough and to make it available on request. And small computations, well, there will be more of them. And I just use Sage Python code, and I include it in the text source of the book, so people can actually display it if they want. That version is not on the archive yet. That's version 2, which is between me and the referees that is being bounced back and forth. And Python is, of course, slow but short and readable. And the nice thing about Sage Tech is that input and output are completely automated, and also that the code can be displayed, as I said. And of course, this is run far too many times. Every time I compile a text file, the tiny computations get done again. So I may have something like that, and when you compile it, usually you will get f of x is less than something. But if you really want to have the code displayed, you can switch a flag in the text code and compile. Also, there's the issue of, is it right to use a computer algebra system in a proof? Mathematica, Maple, Sage are behemoths. The nice thing about Sage is that it's open source, it's peer-reviewed, and it's also very modular. So I'm not trusting all of Sage when I trust Sage. I'm just trusting Python and a tiny self-enclosed part of Sage. Do I have 2 more minutes or? Yes, thank you. All right, some advanced issues that so everything I have told you about before, I've done hundreds of times by now. What I'm going to talk about are very interesting topics that have barely appeared in my practice, but have appeared, or that I have become interested in because of my mathematical practice. So some tiny parts of mathematics are complete theories in the sense of logic, say the theory of real closed fields. So they are systems in which every true statement can be proved from the axioms. And there, of course, in principle, you could write a computer program going through all possible programs and proving the thing. That's, of course, completely unrealistic. But generally, in some cases, there are algorithms. And there are programs that you can find out there. You can say, well, CapCut, compute this, prove this nasty equality for me. You can give it to CapCut, and CapCut will crash, because there are 3 variables, and the computing time is double exponential on number of variables and also exponential on the degree. But, you know, you do a bit of math, and then you have 2 variables, and CapCut is happy and proves it for you in a fraction of a second. Yeah, I mean, as I said, even in these tiny bits of math, the running time has to be very bad, and it's even worse in practice. There are people writing better programs for the cases that we care about. But of course, we cannot even do that, or hope to do that for most of math because of Gödel, nasty, nasty man. Yeah, so there was one such lemma in the first version of my book and none in the current version. but it's something that I came across. It was actually that inequality. I didn't want to bother proving it. It would have taken days and pages, and it would have been meaningless anyhow. Now, formal proofs. Well, what we call a proof when we are taking foundations or teaching foundations is different from what is a proof in practice. What we pretend a proof to be when we are teaching such a class or arguing with philosophers is really a sequence of symbols whose correctness is very, very well defined in a way that can be verified by a monkey grinding an organ, nowadays called a computer. Do we ever use formal proofs in practice? The answer used to be no. The answer is now yes, or we could. There are proof assistants that help us, computer proof assistants that help us to produce formal proofs. I actually haven't used them in Goldbach, and things are not ripe for that, at least not in analytic number theory, but in some areas of math that's now possible. And I hope that within 10 to 30 years, this will become part of common practice in analytic number theory. So time will tell what is practical, and
Okay, so I'd like to talk a little bit about the machine-assisted proof, but in group theory, in representation theory. So, of course, we know that a typical outline of many proofs is to use induction. Now, let me talk about another version of the induction, which is the one that you usually use in group theory. Well, suppose that you want to prove some statement involving some finite or algebraic group, G. Then the first step, which might be very hard, would be to reduce to the case where your G is simple. And here you may want to use the classification of finite simple group, which is another story. But now if your G is large enough, then you try to come up with a uniform proof. But on the other hand, if your G is small, then that will be the induction base. And of course, in either version of the induction, then you have to check the induction base by another method. Okay, so I'd like to talk about one specific example. And the reason why I want to talk about this example is because this example was discussed in a public lecture of Jean-Pierre Serre. So I'd like to talk about the proof of the Ore conjecture. So, well, the conjecture was raised in 1951, and so Ore said that if you have a finite non-abelian simple group, then every element in the group can be written like a commutator. And there were like a lot of partial important results, but finally in 2010, the conjecture was proved by Martin Liebeck, Anne Charlep, Eamon O'Brien, and myself. Well, I should say that even though that we build on the previous result, but our proof is still like 70 pages long. Okay, so how does the proof go? A detailed account of the proof was given in the 2013 Bourbaki seminar lecture by Gunther Mahler. But I can say that one of the basic ideas is to use a counting formula, which basically say that if you know the character table of your group, then, and if you are given with some element G, then you can find the total number of ways that you can write your element like a commutator, which is given by this formula. So basically, you have to show that this sum here is positive or non-zero. That will be enough. Okay, so how do you check the induction base for this kind of problem? Well, if you happen to have the character table W G, then of course you plug in the formula and then you are done. Now, if the character table of your group is not available, but your G is not too large, then you may try to construct the character table of G, and then you use the lemma. And so here's the how did you try to construct a character table of some group? So we start with a nice presentation or representation of your group. You try to go by induction, restriction, and so on. Then you produce enough characters of your group to produce like the entire group of the characters of your group. So this group is actually a lattice with respect to the scalar product of the inner product of characters, and then use the Lenstra-Lovász algorithm to produce a minimum vector in your lattice, which are the illusion characters. And this you can follow the Unger algorithm, which was implemented in the magma. Of course, Bjorn only said something about magma, so okay. But the problem is like some of the groups that we have to treat in the induction base, they are seen too big, like some of these groups, like for instance, I'm sorry. For instance, like the symplectic group of dimension 10 over the F over the fin of 3 elements. So it's seen too large to show to construct the character table. So what do you do for this one? Well, so for this group, then what you do is we have an element in our group, and we run a random search for an element y, such that y and gy are conjugate, and you can see quickly that that means that your G is actually a commutator, and then you are done. So the obvious two questions that you can have about this kind of proof is, well, so how long was the commutation? I can report that it took about 3 years of CPU time on a 2.3 gigahertz computer with a 200 gigabyte of RAM. Well, but maybe the more important question is how reliable was the commutation? Okay, I should go back. So in the cases where we use the character table or we compute the character table, then I can report that the character table is now made publicly available. Then you can recheck it if you like. And in the larger cases where we didn't have the character table, then actually the computer was used to find some element with some specified properties, and then after the computer gives you the element, then we recheck kind of manually that indeed the element has the desired properties. So the computer was used to produce the answer yes, but not to say that the answer is no. And I think my colleague already said about the importance of the machine-assisted discoveries. So the same thing in group theory, and then okay. So I listed some examples, but I think that I should just skip it. Yeah.
Thank you. So I will try to give a wrap-up of this presentation. And my background is a bit different. I'm a mathematician by training, but I've been working in computer science departments all my life. So I'm going to talk a bit of machine-assisted proofs, but more from the point where the machine does all the proof, and try to make some more general considerations. There is more or less a general consensus that this idea of the computer doing proofs started with the proof of the Four-Color Theorem in 1976-77. But actually people had been doing proofs by computers even before that. And this is a particular example that I found from 1966. And let me give a bit of context. This is a paper by Floyd and Knuth in 1973. On a combinatorics, and that talks about the Bose-Nelson sorting problem, which says we have some operations and that we're allowed to use, and we want to find out the smallest sequence of these operations that will sort any inputs of length n. And this is what they call their S of n. And their paper is concerned with values of S of n, and they start by saying, well, S of 2 is obviously 1, S of 3, we can find it. Then they have a theorem that they say this theorem can be used exactly for two things. One of them is showing S of 4 from S of 3. Then they get to the more interesting case of S of 5. So S of 5 is already 9. And their strategy of proof is saying if we make any sequence of 8 of these operations, it will not be able to sort all inputs of length 5. And then they essentially do case analysis by hand, which takes a few pages. Then they apply their fantastic theorem for the second and last time and get the value of S of 6. And the last theorem of the paper is S of 7 is 16. And by this time, I think they gave up on doing things by hands. And they just say, this theorem was proved by exhaustive enumeration on this computer in 1966. And the program was written by Mr. Richard Grove. And the training time was approximately 200 hours. You have no idea what a computer program is, or even what language it was written in. And they conclude the paper with 2 paragraphs about how these proofs were all very frustrating because we don't learn anything from them. It's just case analysis, case analysis, case analysis. At the end, we know all the values of S up to 7 and nothing else, and no idea how to continue. Nowadays, it's been 50 years, and machine proofs are something that's completely everywhere. And I think the biggest area of success is not really what we would call mathematics. It is software and hardware verification. So a lot of you probably remember the 1994 Intel bug where they had to recall all their Pentium processors because of a bug in the hardware. Nowadays, hardware manufacturers tend to formally prove that their hardware is correct before they send it into production. And these proofs are then automatic, nearly almost completely automatically. And the same goes for software. We live in a world where we have computers doing a lot of critical things. One example is, for example, air traffic control software, which at this day it is completely, its safety is formally specified and formally verified, because you definitely do not want two planes to crash because there was a bug in the software that wasn't caused by testing. And the reason that this is kind of successful is because these proofs tend to be really boring proofs that are just case analysis, case analysis, case analysis, and then all the cases are relatively simple, and the computer can do them more or less automatically. When you talk about mathematics, the story is a bit different. So people have been doing also mathematical proofs completely on a computer. And why? Well, I think part of it is just because we can. We're mathematicians, we like doing these kind of things. But also because, as some people mentioned, we are starting to have problems with mathematical proofs of increasing complexity that are simply impossible to do by a human. So it's important to have a computer do them, and it's important to do them in a way that we also can trust the computer and they're not just delegating the error to somewhere else. These proofs typically are everything but automatic. They tend to be mathematical proofs where you have to tell the computer how to do the reasoning and it will more or less check. Sometimes I will try to get to these in the end. You have some proofs that are, I would say, morally wrong if you're a mathematician, but they still work. And there has been a bit of a shift in the style of what we consider computer proof. So the proof of the Four-Color Theorem and the proof by Knuth that I showed was very much this kind of proof where you just write your own program and your program will show what you want to show, and at the end you have a proof. And the obvious problem here is, yes, and then you have to trust the program. And you saw in Knuth's paper there is no program. So if you want to referee this proof, yeah, give me the program. And most referees will not be wanting to read other people's code to see if it's correct or not. So the trend nowadays is a bit more to use theorem provers, and theorem provers are kind of general purpose programs whose job is to do proofs. And they implement some reasoning system in some logic, and then you still need to trust the program, of course. But now we're not talking about a program written by one person to be used once. We're talking about a system that should be stable, that has a stable basis of users, and where many people have worried about this problem of can we trust the program, so hopefully we can. The problem is that then, well, you need to formulate your problem in the logic that the theorem prover uses, and this encoding must be correct. And however, this is more, I think this is easier to do and to ensure by peer reviewing than checking your own program in the most obscure language you can think of. And let me give two examples that come from my research to make these things a bit more concrete. So in 2014, I started working at the University of Southern Denmark, and I started working with Peter Schneiderkamp and Michael Kodish from the Ben Gurion University in Israel, and we started looking again at this Bose-Nelson sorting problem that Knuth was so excited about in the 60s. And in the meantime, so in the 50 years in the middle, there had been one improvement, namely the value of S of 8 was also known, and this was because there was a result from 1972 with a lower bound that happened to give that number as a corollary. And our big contribution in 2014 was we proved that the value of S of 9 was 25. And how did we do this? Well, I'm a bit ashamed to say, but essentially followed Knuth's approach with one difference. There had been a result at the end of 2013 that we realized it had a clever idea that we could adapt to this setting, and it allowed us to be able to reduce the search space very, very drastically. So we could write a prologue program that essentially started generating sequences and could get rid of many of them very, very quickly. The problem is, this was a Prolog program, and if you show this to anyone that works in formal methods, they say, nah, no Prolog. Prolog is not a trusted language, and especially a Prolog interpreter is not something that we want to trust. Well, by the way, this Prolog program took 3 weeks to run, so it was double Knuth's program's time, with the catch that it was on much more modern hardware and running 24 threads simultaneously. But the complexity of this program is that bad. So while it was running, it was producing intermediate results and say, oh, now we only have these 1,000,000 cases to test. Yeah, they're too complicated, so now we unfold them a bit more. Now we have these 1,000,000,000 cases and so on. And when we had around 1,000,000 cases, we did something. We took those cases, we encoded what we wanted to check for each of them as a propositional formula, and we sent the 1,000,000 cases to a set solver, and the set solver returned approximately at the same time saying none of these cases is solvable. So we had 2 semi-independent proofs. The problem is, well, can we trust a set solver? And this is actually a very non-trivial question that I'll discuss in the next slide. The other problem is, well, now we're encoding stuff in propositional logic. Is this encoding correct? And in our case, it wasn't quite a number of times. So the final version, we believe it is. The referees also agree that it is, but it's still a problem. And in the end, we did, well, we implemented the algorithm in a theorem prover, and we used the theorem prover to prove that it was correct, and we got a computer program that we know it cannot have any bugs because of mathematical results, and you run it. And you might ask, well, why didn't you do this at the start? Because this program is much, much, much slower because of how it is built. And the only way to make it work in reasonable time was use the output from the Prolog program as input, that this program will then say, well, I don't believe you, but so I'll just check what you're telling me. But checking that you can get rid of this case for this reason is much easier than finding out that you can do it. So something about set solvers. Where am I supposed to point? I do believe I had one last slide. Anyway, I can talk about it anyway. On the area of set solvers, yes. So a set solver is a program that takes as input a propositional formula and tries to find out whether it is satisfiable or not. And set solvers have become extremely popular because they are extremely good and they can really solve formulas with millions of variables and huge sizes. But they have one problem. They are designed to be very, very efficient and very, very fast. And no one can understand what they're doing. So, and when they say, yes, your formula is satisfiable, you can say, okay, give me a satisfying assignment, and it will, and you can check it. And if it says the formula is unsatisfiable, then you say, why? And it says, because I say so. And you say, well, let's look at the code. No, definitely you don't want to do it. Also, proving a set solver correct is completely out of the question because they evolve faster than you could do it. So the question is, how do we trust these answers? And people started worrying about this some 10 years ago because, again, you don't want your plane to crash because of an error in the set solver. And I started devising formats that the set solver could say, no, your formula is unsatisfiable, and here's a trace of my proof. The problem was that in order to verify these traces, they needed programs that were as complex as the set solvers and that had exactly the same problems. And about 2 years ago, I was again with Peter Schneiderkamp in Lisbon, and we met with João Marques Silva, who is an expert on set solving there, and we started talking about this issue, and we realized that the techniques we used for this problem to make this certified program run could probably be adapted to the domain of set solving. And it was kind of an interesting result, and a lot of people built upon it since then. The end of the story is that nowadays we actually have ways to verify also proofs of unsatisfiability in feasible time. And where does this connect to mathematics? So what I call the morally wrong use of set solving is that people now have started applying them to mathematical problems instead of hardware circuits and computerish things. And what they do is they say, well, if this mathematical theorem is false, then there is this finite counterexample. encode it in propositional logic, send it to a set solver, wait a few weeks for the results. The set solver says no, therefore there is no counterexample, and your mathematical theorem is correct. And you have the same problem as Knuth's proofs, yes. And what did we gain from this? We have absolutely no intuition to why the theorem holds. It just, yeah. And I had an example. So we apply this to the largest proof at the time, which was the Pythagorean triples conjecture. I don't know if anyone knows about it. It asks whether you can color the natural numbers in two colors such that no solution to the Pythagorean equation is monochromatic. And the answer is no, and the set solver that's managed to find the answer and say no, output 400 terabytes as the justification, which is, of course, completely unfeasible to verify by hand. And I've heard at the moment that there is an even bigger proof around, but I still haven't seen it, so I still make the claim that we checked the largest proof in existence. And I think that's what I wanted to say. Thank you.
We're open to questions from the floor, and if you put your hand up, I'll try to see you, and one of our staff will bring you a microphone. Yes.
Systems that check if formalized proof is correct or not are, well, being developed in many cases, and they are able to check proofs in different branches of mathematics, but they also suppose mathematics for they to work. I mean, these proof checkers have algorithms that should be correct and so on. And my question is, what kind of mathematical power we need to have that these algorithms used are in fact true? And this question is because in order to avoid the possible vicious circles. Suppose you want to check a proof about, I don't know, analysis, and the algorithm you use is only valid not to say over the primitive recursive arithmetic, but you need something higher level. I mean, what's the status of this? I mean, how much mathematics do you need to completely check a proof? It's all primitive recursive, you need more. Is this a problem in practice? Just a philosophical question? It's a very broad question, so.
Luís, do you want to have a first go at this one?
Yeah, I'm not an expert on that part of the foundation, so, but let me try to give some answers. So, the first thing is the problem of the correctness of the software itself. And usually what a lot of systems try to do is they have what they call the trusted kernel, which is the part that you really need to trust. And that should be small enough that you can read the code and several people have done it and understand it. And then you make a model of the system inside itself, and you can actually prove a large part of the system correct. So this solves the problem, at least from the practical side, that you can trust you don't have implementation bugs and that your algorithms are correct and that you're doing what they're supposed to do. In terms of the mathematical requirements, the model theory for the systems that people use for powerful stuff tends to have quite strong assumptions. So I don't want to say anything concrete because I'm not completely sure, but they tend to be quite, you are relying on a quite powerful theory, yes.
Would use just a small part of mathematics to show that proof is correct. I mean, you cannot use the axiom of choice to prove some combinatorial thing. It's weird. So,
I think there's also a pragmatic point of view. So Hales told me that he used whole light as his main vehicle for the Kepler conjecture proof, not because whole light was logically more powerful than anything else. It's just that he happened to have a more complete library for the sorts of real analysis he needed. And so in practice, I think, as opposed to theory, which is a good question, in practice the answer is more a pragmatic one. How much has been done? How much more do I need to build to get there? And in particular, there's now a lot of real analysis there in whole light, which interestingly is there because Harrison was hired by Intel as an outgrowth of the Pentium bug. So the Pentium bug, in fact, has ultimately contributed to the formal proof of the Kepler conjecture. But it's a case of what is there that we need. And for example, there's very little encoded topology and so on. And even real geometry is missing, whereas there's quite a lot of work in real analysis. But that's just because that's where people have done things. And so there's an awful lot of algebra in order to support the Gontier proof of the odd order theorem implemented in Coq. So if I wanted to do something in group theory, I'd probably use Coq. If I want to do real analysis, I'd probably use whole light. Not because one is more powerful than the other theoretically, but just because of what's been done in them in the past. So I think that's actually more of an important question in practice than the theoretical question which you asked, which is still very important, which I don't think any of us knows the answer.
But I also think that whole, yes, exactly. But I also think that whole light, as the name indicates, has a tiny, well, deliberately tiny kernel that fits on two sides of a large postcard, essentially. Yeah. The kernel, I mean, but it was always thought that a formal proof would be like that. It's that's the least of our concerns. Checking a formal proof should be something doable by a very stupid monkey on a very stupid organ. It's everything else that is more problematic because you need to translate higher concepts into that.
Yeah.
Okay, thank you.
Yes. That microphone's coming towards you.
The first speaker did mention a series of cases in which the use of computers would help in doing his scientific research. He mentioned, but I didn't hear much comment on this to now, the fact that computers can be very helpful in generating conjectures. And this has been tested in Montreal, in my group at Gerard, where we considered graph theory problems. And we built a system called autographics, which is designed in order to find new conjectures in graph theory. The conjectures are obtained by generating initially some samples and then using meta-heuristics to obtain better conjectures. And one of my students, Mustafa Aushish, did in his thesis consider all cases with 20 graph theory invariants. So he took some well-known invariants, chromatic number, clique number, maximum degree, minimum degree, and so on. And he looked at all conjectures which were of the form one invariant, one of the four operations, another invariant, and it is asked to find best possible lower bounds and upper bounds on these expressions. And there are 1,520 cases, of which we obtained answers for the conjecture. We could prove the conjectures. About half of the conjectures were proved by machines. They were rather trivial in some cases. And then 300 to 400 conjectures were proved by mathematicians in various countries, mostly Serbia and and Belgium. And 3% of the conjectures turned out to be false. 1.5% turned out to be already be known. And 6% of the conjectures could not be proved either by the computer or by ourselves. Now, I would like to ask the audience and the speakers in particular if they have some experience on finding conjectures in discrete mathematics and what they think about the use of computers in that respect. Thank you.
Thank you. James, you spoke about using computers to generate conjectures and generate lemmas.
Yeah, so in my experience, I haven't used computers to generate the main result conjecture, although there's certainly examples. Bjorn mentioned the Birch-Wellington-Dyer conjecture as now one of the most central problems in number theory that arose initially from computations, and belief in the Riemann hypothesis was made much stronger after computations, and things like the twin prime conjecture and Goldbach's conjecture also initially led quite a lot by computations to give confidence. In my experience, I guess, I've used computers very much to lead the guess for conjectures for auxiliary small lemmas. So that's where I've personally found computers very useful, that I know that I need some intermediate technical statement that's of a certain approximate form, but pinning down the precise correct statement is often very challenging, and using a computer to test out several different possibilities or variations and to let the computer lead me for what the precise statement of that intermediate lemma would be is something that I've certainly used and I found useful. So I guess that's my experience of using a computer to lead me in the right direction. It's always been for small lemmas. I don't know if the rest of the panel have anything they'd like to add.
Bjorn?
Well, could you repeat the very end of your question again? I'm not.
Experience in
have you some
using
experience
computers?
in
Sorry.
generating conjectures by a computer in various fields of mathematics? And how do you judge this experience, if any?
So the question was about how my personal experience with developing conjecture,
Yes.
generating conjectures
Yes.
with a computer. Well, I mean, I think I've done it a couple of times. I mean, I can mention one example maybe. This is about the probability that a polynomial of degree n has no real roots, where n is even, of course. We know what happens if n is odd. We know what the probability is that there's a real root. But if n is even, you can ask, for large n, the probability of having no real root tends to 0, and you can ask what's the rate at which it tends to 0. And, well, I mean, I did some numerical Monte Carlo simulations and tried to, well, anyway, we eventually figured out, conjectured that it should be n to some exponent, and with several co-authors, we were able to prove a theorem along these lines, except we didn't know exactly what the exponent is. Although recently, I think we thought it was around 0.76 or so, but recently I've heard that there's a theorem that maybe it's actually that's been announced that it's actually 3/4. So anyway, there are all. I mean, I know a lot of people who've generated in various branches of mathematics, generated new conjectures. I think it's present in a lot of different fields now. So, yeah. But I haven't heard of something as extensive as what you and your group have done in the sense of generating huge. I mean, exploring a whole landscape of different possible conjectures and trying to prove them individually, all of them. But yeah. Okay, thank you for your question.
Thank you, yes. Yes, front row, please.
Thank you. So my question is, I know that there are some groups that are currently developing tools for Isabelle and Hall, where you essentially you do a part of formal proof, and then you write an algorithm, and then Isabelle that you verify then with the formal verification of Isabelle Hall, and then the Isabelle Hall generates code that it's compiled, and then it's run, and gives a result that is therefore is plugged inside the formal proof again, and this is used to into this. I know that they did. There is probably a PhD student that did this for the to verify formally the Lorentz proof of the proof of the existence of the Lorentz attractor, and I think that. And I wanted to ask if you thought that this would be a possible standard for the future into computer-assisted proofs.
I'm not sure I fully understood the question. You're asking about whether there should be a standard for proof in terms of...
So essentially you have Isabelle and Hall that checks that everything works, and then you have then you check that the algorithm that you are going to run to estimate your constants is rigorously, it's formally correct, and then Isabelle Hall generates the code is run, and then you get your constants, and then you plug them back into your proof that is again checked by Isabelle Hall until you get your proof. And so every step and the algorithm and all the computation are formally checked. And I want, because it seemed to me that many of the issues that were discussed today were should we trust or we shouldn't trust computer-aided proof. And this seems to me as a computer-aided proof in different many levels. So we have the issue of checking it formally, we have the issues of having the computer aiding us to estimate constants or to check a finite number of cases. And it seems to me that this kind of approach would be a feasible approach. But the biggest problem, it seems to me, is the steep learning curve that you have to do to learn Isabelle and Hall and all this machinery.
Luís, do you want to first go at that one?
Yeah, so there are two different aspects there, so I'm not sure which one you're referring to or both. Yes, so there are two things you can do. One of them is you can, so as you say, you can specify your algorithm in Isabelle, and it will produce an implementation that's guaranteed to follow the algorithm precisely, so that you can, if you any properties you proved about the algorithm, you know that your program will have them. But in some cases, you can get by with something simpler, which is what we did, for example, in our cock proofs, which is just say, oh, I need a value here with some properties, and I have no idea how to find it. So I just use some code that I don't need to trust. It doesn't need to be correct, but it will give me a value. And when I get the value, I check that this value does have the property. And this way, you don't care how the value was obtained. You don't need to worry about it, because even if the program is wrong, you are still checking the value. So if the value is wrong, you'll find out. And if the value is right, it's like those students who make 2 arithmetic mistakes and get to the right answer by accident. But if all you need is the answer, it still works. So, I mean, and I think this is something that's becoming more and more used in computer proofs, because people realize what you were saying. If you want to do everything inside Isabelle or inside any theorem prover, first you need to make the theorem prover extremely powerful, and then it gets more and more complex to use. And Isabelle in particular is known for being very, very easy to use. So for having a very slow learning curve, and you can do very much by knowing very little.
Thanks. But I also believe that the proof of the fly-spec conjecture does a bit of that. There's a certain amount of importing computations done elsewhere, still verified, but done elsewhere. So there's an amount of that, I think.
But I think that what's happening now, that was the thing that made me, I don't really know so much about the topic, but is that Isabelle generates the pseudocode and then it's compiled. So you know that the computation done elsewhere is also formally correct, up to correctness of the floating point and of the implementation. So Isabelle, so you have to implement a floating point inside Isabelle. You have to implement all this stuff inside Isabelle so that then it checks that everything works fine in your outside in your outside computation. But I'm just
yes. Larry Paulson's done a lot of work with his Isabelle-based Metatarsky system to prove the correctness of floating point computations. Yes.
Yeah, just to add something, I think that sounds like a great gold standard to have. The unfortunate reality is that we're miles away from anything like that. At the moment now, for as sort of maybe the lay mathematician on the panel, it's unfortunately the case that it's unrealistic now for a working mathematician to be hoping to directly implement most of their program, most of their proofs in a formal proof checker. This would be a great dream to have for the future. The sort of setup that you've outlined is maybe what the gold standard should be, at least for small computations, that it's easy to run individually. But the unfortunate situation is that at the moment, for the day-to-day mathematician, they're not going to be writing their proofs in formal language, and we have to go a long, long way, both to have more things that we can do in formal solvers, and also to bridge the steep learning curve for the day-to-day mathematician if we really want to start making the formal checking on proofs a more common thing.
Looks like something that could happen now.
We're certainly moving in the right direction.
That's a very, very good point, James. We're certainly moving in the right direction, yes. Is there, yes.
Most of the time, when in the process of referring a paper, you have to check some calculation on the correctness of some calculation, some expression, and you cannot do this by hand. You have to use computer algebra software, for example, and sometimes the author, under request, send you some files, be it in Maple, Mathematica, and so on. So the question is, the problem is that sometimes you don't have the copyrighted material. Mathematica is quite expensive, or Maple, and you have to check the correctness of the expression. Sometimes ago, there was an idea to design a program which could help to convert, let's say, a code implemented in Mathematica so that it can run in Maple and vice versa. So my concern is to have a feedback to know if such thinking has evolved, if there is any consistent application which can help to convert a program implemented in Maple into Mathematica, or even in open source software like Sage. Thank you.
Harald, I think you had some, or was it James, about proprietary languages versus open source?
I mean, I agree with you saying open source languages, but yes.
I don't know offhand if such things exist for something that would automatically convert a Mathematica program into a Maple or some other, but it would be nice if such things existed.
But
and maybe it should be on the the burden should be on the producers of the proprietary software to provide such conversion, because I mean, if they want people to use their software and trust it, then it'd be nice if they were something that could be exported from them. I don't know.
Of course, but it's even better to write one's own Sage code and see whether it gives the same answer in somebody else's mathematical code.
Although, at the risk of sounding somewhat negative, there's certainly going to be very big challenges if you want to do anything like this, that some of the algorithms within Mathematical or Maple are proprietary.
Yes.
It's an unfortunate situation that, depending on precisely what bit of mathematics you want to do, some computer algebra packages are much better or worse suited to you. So some people don't have a choice, but they have to work with Maple. Some don't have a choice, they have to work with Magma. Some don't have a choice, they have to work with Sage, based on the sorts of programs that you're doing, because the same implementations, there's not the same implementations of the overall algorithms. Obviously, in a ideal, idyllic world, we would all be using the same open source software, but unfortunately that's not the case. But something like this, at least for small computations, if you're not doing more sophisticated algebra, which really relies on certain proprietary packages or individual packages which are unique to a certain computer system, for simple basic computations that you can do in any system, I certainly think it would be a very beneficial thing if we could have some simple code that's interoperable and can be used essentially in whichever package or computer algebra system you like most.
Yes. Well, Sage, which is really a large collection of packages by very many people, has proved in my practice to be sufficient for practically all of my needs. I've forgotten the last time I had to use Mathematica, to mention one thing, but it was many years ago.
The Open Math standard will generally let you move expressions between one system and another. The problem is moving the semantics of the expressions. For example, different languages will disagree about where the branch cuts of elementary functions lie and so on. And then there is, as I said, the question what the algorithms in the algebra systems actually do. And it's very hard to find a formal specification for things like symbolic integration algorithms. And indeed, we are guilty of that as mathematicians. We talk about the greatest common divisor, when in fact we should talk about a greatest common divisor. And it's not always clear which they will return in multivariate cases. We've got time for one more brief question.
I want to comment on the same. I think translating the language, maybe not so hard, but like he said, the semantics and the algorithms themselves. And I think the problem with using expensive software is not that they are expensive, but that sometimes a computation depends on using an algorithm that is closed source. And it's not about price, but it's about being close. And then that's very dangerous, because the companies don't let us check that the computation is correct. So that's a trap that we should avoid. But also sometimes some papers are published which depend on some computation, and not always the programs are published or they are easy to use or to reproduce. And sometimes this, I think we should be more careful about this, about the reproducibility and about being able to actually check.
Yes, at the very least, yes. At the very least, we should give pseudocode, and then if people want to implement it themselves, it's even better. But oh,
yes.
Thank you. So this is addressed to all of members of the panel. Vladimir Voivodsky had a very strong opinion on proof assistance, and in the last years of his life, he was very vocal about the need for new foundations for mathematics. I think I call them univalent foundations. So I would like you, this panel, to comment on this, because he has left us since. Thank you.
They don't have any comments to make on that one? Harald?
no, I don't know enough about that. It's very interesting, but I don't know enough about it.
Yeah, same here. I'll defer to the others.
I think the answer is the jury is still out on that one, I think. It's a very impressive claim. I've heard it myself, but I don't think it's yet been vindicated in practice, yet. And I think on that note, we have to bring this panel to an end. Can I thank all the panelists for their wonderful contributions? And thank the audience for their questions from the floor, and remind you the next panel starts at 4:30. Thank you.